Like the two-sample t-test features a parameter that is merely the difference between two population means, the two-sample z-test for proportions analyzes the difference of two proportions. Suppose someone claims that proportion 1 is greater than proportion 2. The null would be p1 is less than or equal to p2, and it would collapse to p1 equals p2. Now listen up, this is very important and it can get tricky. We always need a sampling distribution from which to work, and it needs a numerical mean. Once again, our mean will be 0. Zero difference between the proportions is assumed at the beginning of the problem. But now we have a dilemma. What in the world do we use for the proportion values in our formula for the standard deviation of the difference of two proportions? You might guess to simply insert each of the sample proportions after we take the samples. But if that was your guess, you'd be wrong. But you'd be close. Let's reason this through. If we assume the proportions to be equal, then samples of the same size would produce equal standard deviations, equal variances. Recall from the two-sample t-test that such a case allows us to pool the variances. And this is exactly what we do in this test of the difference of proportions. We assume the null is true that both population proportions are equal, which is pretty much like sampling from the same population. So we merely combine our two samples into one pooled sample and use this pooled p-hat as our estimate of what the same population proportions would equal. For example, if one sample of 60 had 48 successes and the other sample of 40 had 28 successes, our pooled p-hat would equal a combined 76 successes out of a total of 100 observations. Our pooled p-hat would equal 0.76. We'd use this value in the standard deviation formula. Stay with me, we're not done reasoning this through. Why, might you ask, do we not just average the two individual p-hats from the two samples to get a pooled p-hat of 0.75? Well, I'm glad you asked. We must assume the null is true to calculate a z-score and p-value, so the two samples are assumed to come from populations with equal proportions. But which of the two samples is likely to be more accurate? Correct, the larger of the two samples. This sample proportion was 0.8. The smaller sample proportion was 0.7. Since the larger sample is likely to be more accurate, we need to give it more weight and use a pooled p-hat above the averaged p-hat of 0.75. Pooling the two samples automatically gives the larger sample 60% of the weight in this case, and the estimated pooled p-hat is 60% of the way from the smaller proportion of 0.7 to the larger proportion of 0.8. This is how we arrive at a pooled p-hat of 0.76, the best possible estimate of the unknown proportions if they are equal. So remember, the null is assumed to be true. We must estimate what these equal proportions are. We do this by pooling the samples together to estimate the same proportion, and pooling automatically assigns more weight to the greater sample size. Alrighty then, on to the next video.